If you have ever had the dubious fortune to look at the Maze Runner code, in the configuration are these lines amongst very many others, and in there are these mysterious numbers. And I was quite reasonably asked the question, well, how on earth did you get those? And perhaps more to the point, why are they fractions and not, I mean, magic numbers are bad enough, but magic fractions, nobody needs that. So anyway, that's what we'll be having a look at today. If I can find my presentation screen. Right, so the Maze Runner software, well, no, to go back before that, when the idea came up of making a club robot, the idea was to give people a good head start and make a basis for them to build, whatever they needed to build, and avoid the hard work of the design and component selection and that sort of stuff. And then inevitably, that's no good without software. And so I decided to produce a software suite. There's two currently published, and one of them, Maze Runner, contains everything you need to do to run the mouse in the maze. But it also contains a bunch of other things. And because I'm a devious person and a former teacher, it isn't just intended to tell you how to run the mouse in the maze. In fact, if you've looked at it with a view to just running a mouse in a maze, you'll be quite disappointed because it's much more complicated than that. And it was the code pretty much deliberately was intended to achieve more than just that aim. Only one of the aims was making the mouse run in the maze. Another was that there's also to show people how to configure and test your robot. And this is generic. It's not just about the Mars bot. It would work with almost any other similarly driven robot. And buried inside there are any number of hints and tips and clues and guidance as to how I think you might want to do things in the software. Now, let's be clear. This is how I think you should do it. It's not necessarily the right way or the best way. It's just the way that works for me and that I'm familiar with. And that led to quite complicated code. And in retrospect, it was perhaps a mistake to make it that complex and to hide things away. But nonetheless, people have found things and used it successfully. So, it's achieving at least some of its goals. And the whole thing is about training and learning. It's not a dish it up McDonald's takeaway job at all. So today, what I want to do is to go over a few things, specifically about the control of the robot. I want to describe how the robot is controlled in the software and what the control loop looks like, or control loops. I want to see how the robot responds. And in particular today, we're going to be talking about those magic numbers, the feed-forward numbers is what they are. I'm going to show you how you characterize the robot response, how you work out what those magic numbers are and where the numbers come from, and how you use them in the robot. And again, I should point out that this will apply perfectly well to any other wheelchair-type, non-holonomic wheeled mobile robot or tank or whatever else you wish, right? It'll all work the same way. In terms of the control of your robot, you have certain requirements. If you want a well-behaved and predictable robot, you want steady state errors to be small. They'll almost certainly never be zero, but you certainly want them to be small. You want your control system to be able to cope with all kinds of disturbances. The battery voltage can change. There could be steps in the surface, or the surface friction could change. You want it to also to be responsive and stable. So you don't want it to suddenly take off and do odd, strange things, or to discover that the faster you go, the less stable it is, or these are the things that you see which are problems. Now, if you're just building a robot to faff around with at home, you might put up with quite a lot in terms of poor response. But if you want to run in contests, it soon becomes apparent that you have to pay a lot of attention to these things. And the faster you go and the further you go, the more important it is to get these things right. So inside the software, there will be controllers. And their job is to make sure that these various aims are met. And the controller's job will consider for the time being just the forward motion control. The same thing applies to rotational motion and steering and all the other things, but just for the time being, we'll consider the forward motion. And the controller's job is to put an appropriate pulse width modulation duty cycle to the motors. And a naive approach would be to use the PWM setting in your processor and say, well, I want it to be 50% or 70% or whatever. But that's not going to do you any good if the battery voltage changes, because 50% of 6 volts isn't the same as 50% of 7 volts. And as you increase the load, it's going to drag the battery voltage down, and so you get a response that changes. UKMARS software sets an actual voltage, and there's a little bit of fiddling in the software if you go hunting for it, which compensates for battery voltage. So if you say you want 5 volts to the motors, you get 5 volts to the motors. And the battery voltage, within reasonable limits, won't matter. If you want to drive the whole thing at a constant speed, you might, and I've seen it done, just say, it's going too fast, I'll stop driving it. It's going too slow, I'll start driving it. In fact, I used to work with somebody who operated their car that way. It was most disturbing. And that's called bang-bang control, and it works, not terribly well, and it'll wreak havoc. Your gearbox will be slammed in forward and then slammed on the brakes and then slammed forward again and so on. But it'll work. It turns out, though, that we can do better. So first thing is to try and discover what's going on with the robot itself. And so if using the software that's there, you can apply a constant voltage to the motors. And if you apply, let's say, 3 volts to the motors, which is the green line in the middle on this chart, excuse me, you will see that the speed increases. And eventually, over a period of time, it'll reach a constant speed. And indeed, if you apply any constant DC voltage to the robot, you will see pretty much the same response. The robot will start from nothing, ramp up to a constant speed, and stay at that speed, unless the load changes, if it goes uphill or downhill or whatever. And there are interesting things to notice in this chart. One is that the shape of the response in all cases is the same. In fact, the grey line is a plot of an equation, which you will see later, which very closely models the behavior of the robot. It's a first-order exponential. Another thing to note is that regardless of the voltage that you apply, it takes the same amount of time to get to constant speed. The axis on the bottom is time, not distance. And after 5 time constants, let's say 500 milliseconds, you can see that regardless of the voltage, the robot is pretty much at its final terminal velocity. And in fact, 5 time constants, if I remember correctly, is 99% of the target. The other thing that you'll notice is that as the voltage gets higher, the starting behavior gets more weird. And it doesn't take long to work out this is probably wheel slip. After all, you're sitting there with the robot, you're suddenly going to pump 6 volts into the motors and try and make them turn full speed. Something has to give. And in fact, the wheels slip, and so they appear to go extra fast. Then they catch and slow down, and eventually it it comes back right. So the most valid results are up to about 3 volts, but actually the behavior is the same. If you had properly grippy tires, perfectly grippy tires, you'd see the exact same smooth response across all voltages. Do chip in if you have questions at any point, because you'll probably have forgotten by the end. So in order to get a nice proper control out of the whole system, we use a controller, so-called. And you will have come across PID controllers, proportional, integral, and derivative controllers. Almost certainly you will have looked up stuff about this, you may use them. And without casting aspersions on any individuals, it's quite possible that you don't really understand what's going on. But not to worry, there are libraries and there are simple instructions, and you can plug numbers in and make things work. It's not that easy, unfortunately, to make a PID controller work. Underneath, you'll see a control diagram, a basic control diagram from UKMARS bot. And you can see something which confuses people quite a lot, and which sometimes I struggle to explain, possibly because I'm just no good at explaining it, or possibly because people have a preconceived idea of what I'm talking about, and so they've already stopped listening. That happens a lot. I don't know. But the thing to notice is that the control in UKMARS bot is a position control system. Right? Now there's an input there, which is speed, and there's an output, which is speed. But that's not what's controlled. What's controlled is the position. Because here, if you can see the sluggish mouse, the required speed is integrated to make a position, because distance is just the integral of speed, right? And the measured speed from the encoders is also integrated to give a position. And it's the position error which goes into the controller. And the controller is just a PD controller. There's no I term, because you're never controlling the position long enough to require the benefits of an I term. It's a very, very simple, deceptively simple system. So what happens is we have a demanded speed, and we know how often we're running the control loop, so 1/500th of a second. So if I want to go 500 millimeters per second, then in one control loop interval, that means my distance must move forward by 1 millimeter, right? And so I add a millimeter to the position. The robot, however, may have moved more or less, and so I get a distance back from the encoders, and I subtract that, right? So I want my set point to move on a millimeter. The robot's only moved 0.5 millimeter. I've now got a 0.5 millimeter error, and I use that to work out a voltage to drive the motors. That's not what tonight's about, but that's what's going on, right? You'll see it in a bit, so it's worth explaining. And the trick here is to tune these controllers to make them behave well. And if you've ever looked at online tutorials, or if you've ever looked up on Google how to tune a PID controller, you will almost certainly have come away dismayed. In principle, I quote unquote understand controllers. I've done courses, I've done the maths, I've designed them, but it still leaves me cold. It's something that you really can live without having to do if you can possibly help it. And indeed, if you go and have a look at instructions on how to tune controllers, here's a fairly typical thing, and it'll tell you that if you're not careful, you get oscillation and you never reach the set point. It'll tell you that if you get things wrong in the other direction, it'll take forever to reach the set point, and you're looking for a response. And there are various guides as to what constitutes a good response, right? So under some circumstances, this center one here might be a good response. There's a little tiny bit of overshoot, but it gets up to the final value fairly quickly. This one here, bottom left, gets to the final value sooner, but overshoots for a little bit, right? And so not only do you have to understand how the various parameters of the controller affect these responses, you also have to decide which of these responses is acceptable to you. And it's just hard work. Not only that, this particular article, which is one of the top 10 listed when I searched on Google for tuning control loops, and this picture is stolen all over the place and used in other people's descriptions. This is a PID controller, remember? Where's the D term in this? Right? There's a P for the proportional, there's an I for the integral, and there's no mention at all of how the D might make a difference, because it's using a different mathematical model to the one that you may have looked up a statement about the maths of the control loop, and it'll talk about KPE and KD times E minus E dashed and all that sort of stuff. But here they're combined into TI. And anyway, to cut a long story short, PID control loops are a nightmare. People use them, people tune them, they tune them badly, and they don't understand what's happened when they've done it. So that's the problem, okay? Well, what happens when we go to try to make your robot do something? So this is a Mars bot, a bog standard Mars bot. It has 20-to-1 motors, and I have got a reasonably well-tuned controller running on it. And if you just try and absorb what's going on in the chart here, the orangey red line is the set voltage. The robot has been asked to travel 50 centimeters at a speed of 1 meter per second and an acceleration of 3 meters per second squared. This is a test you can easily do because 50 centimeters, is only the width of a decent sized monitor, or it's 18 inches. It's not far. You can do it on the tabletop right in front of you. You don't have to scrabble about on the floor. It's an easy test to do. And the dark red line is the speed as recorded from the robot. Okay. The yellow line, so it's a pretty good match, and if you got a result like this, you'd be reasonably happy. The yellow line is the control output from that PID controller that I showed you earlier. It's the voltage produced by the PD, I should say, the PD controller, and you can see that it goes up with speed. When we get to the target speed, it stops increasing and it's fairly steady. And then in order to break the robot, it goes down and slowly decreases. By the way, this is 0 volts, right? Voltage is on the right-hand side. And actually the control voltage will go negative if it wants to, in order to try and get enough braking force out of the robot. That's another thing that folk struggle with. You may have to put negative voltage across the motors to brake hard enough. The green line is the kind of the smoothed out version of the yellow line, right? So if you imagine I just drew a straight line through these yellow points, I'd get that and that and that. And we'll come back to that. So this response, the dark line, compared to the set point, the red line, doesn't look too bad. But if you're fussy, if you want things to go well, and you examine it carefully, there are some areas of concern. Here, at the start, nothing happens for a while. Well, that doesn't sound right. Why would nothing happen for a while? Well, remember that the controller outputs a voltage based upon the error that it sees. And until there is an error, it can't put out a voltage. The implication of that is that the output is always wrong. Without an error, there's no output. right? And so the error has to build up here, and you can see the output voltage building and building and building and building until finally it starts to move. And then it finds itself in danger of overshooting. It's catching up too quickly. Look, the slope of this is too high. And so it has to kind of come back and sort itself out. By the time we've got to here, it's sorted itself out. Now, this is only 75 milliseconds, but milliseconds count. And then finally, it starts to kind of get things right. And then it comes to the point where it's got to stop accelerating and travel at constant speed. And now you can see that it overshoots, because you can't suddenly hit the brakes and get the speed just dead right. The controller overshoots, compensates, comes back and starts to converge on a nice steady value. And then it's just got the hang of that when you tell it to hit the brakes. But the robot carries on. The controller responds as the error grows by bringing the voltage down more and more and more. And then finally we sort of settle on a fairly steady response. Now, this is all over in 800 milliseconds, so it may not seem like a big deal to you, but I'm assuming that at some point you want a better performing robot. And these are things that can be of concern. So this yellow line, the green line, I should say, which is the average of the controller output, suppose I worked out values for that green line and applied them to the motor, but no controller. So the controller's doing nothing. The controller is just sitting there minding its own business. And instead of letting the controller supply voltage to the motor, I calculate a voltage and apply it directly to the motor instead of the controller output. And that's voltage is called the feed-forward voltage. I calculate what voltage is needed to make the motor run at a particular speed. I know that if I want the motor to run at 1 meter per second, or the robot to run at 1 meter per second, I'm going to have to put a little under 4 volts into it. So forget the other stuff. If I applied 4 volts, the robot would run at 1 meter per second. I can work that out. So I can apply that 4 volts. And also for all of the intermediate speeds, for every speed in between, I can apply a voltage corresponding to the speed, and the robot does a remarkably good job of tracking my voltage profile. In fact, if you saw it run on the ground, you wouldn't be able to see the difference between this and the controlled output. It does very nearly 500 millimeters, and it does it at speeds which are remarkably close to the desired speed. But it's not actually under full control. The yellow line is what the controller is doing to try and correct for the mistakes in this green line. And it soon throws a hissy fit and saturates out at 6 volts and says, I can't help, I can't do anything about it. But it's not actually applying any voltage. This is I'm just recording what the controller wants to do. I'm not allowing it to do it. So there are some other interesting things. This green line does not start at 0. It starts up here at 1 point something volts. And there is this step behavior here, which we'll look at those in a bit. So now, remember, I've got a controlled output. This is the controller only, and the controller tracks the changing speeds very well, but has problems when there are sudden changes to the speed. I have a different way of putting voltage into the motor, which is quite good at getting the speed right, and very good at coping with these changes, which were a problem before. So now I've got 2 different ways of applying voltage to the motor, and they are good at different things. So what happens when I combine them? Well, that's what I get. I'm applying the feed-forward voltage, which we know can pretty much get the motor to do what we want it to do. And then the controller's only job is to fill in the errors left behind by the feed-forward control. So it doesn't have to wait for a big error, because there isn't a big error. And this line and this line, if I just go back and forth a bit, are tracking significantly better than they were before. But by combining the two methods of driving the motors, I can use one to fill in for the bad points of the other and vice versa, and I can get a very, very good control of the motor. This shenanigans up here is just, it's the run that I chose. Other runs would have shown different errors, but I wasn't going to spend all day looking for a perfect one because life's too short. So the yellow...
You said it through with questions.
Yeah.
Is it okay? Yeah.
Yeah.
Very briefly, I don't really understand why there's that initial step in the feed-forward voltage. Why doesn't it start at 0?
You will.
Okay, right.
Right. It's a good question. It's a very good question, but I'll explain it in a bit.
So I assume that when you were looking at the feedback controller, I mean, there's going to be a natural lag in the performance because it's, you're feeding back old data. You've also
It's not just the control loop lag. Yes, go on.
I guess you've also got sensor. Your sensor resolution's always going to be limited. It's not going to be at a very small time steps. It's not going to be.
All these things are true. The poor sensor resolution are largely what's responsible for these oscillations that you see. Right, because it's only doing like 3 counts per millimeter, whereas on my contest robot Decimus I've got I can't remember 100 times that. Right, and so the opportunity to get the answer right is much better. There's lack of precision means that there's going to be some oscillation.
I guess as well, I mean, people, I guess, to try to pump up maybe the derivative term in order to get rid of the...
Yeah, and it's a mistake because you end up with a controller output. I mean, the thing is, right, that when you look at it on the ground, you can't tell. Right? If I was going to video the tests, but a fit of laziness overcame me, and you would, if I videoed the feed forward only, the feedback only, and the feedback plus feed forward, and showed you the 3 of them and asked you to put a coin in a slot, say which one you thought was which, you'd get it wrong. You can't tell the difference, right? Because, well, for all sorts of reasons, just because people are pretty poor at that. But when it comes to running at top speed around a maze and missing a post by 2 millimeters, several meters per second, trust me, this is a difference you want to have. So a lot of these variations, they look quite pronounced on the graphs and charts, but you wouldn't see them by just with the unaided eye. That's why I go through this rather than just say, I couldn't change a parameter and run the mouse and say, look how much better it is. I could do that with the steering, but not with this. And so when you say, well, people respond by changing the KD term or the KP term, they'll do that, but you have to make quite gross changes before you can physically see a difference. By then, your controller's probably shot. And so if you increase the KD term, KD is very, very sensitive to noise. So these ripples here would produce huge spikes in the output. And that's not good for your battery. It's not good for your motor. And in the end, it's not actually any good for your control either. So what you see on here now is the yellow line is just what the controller is trying to do to fill in. And if you look at it carefully, you can see there's still a little bit of a delay here, and so it's putting out a little voltage. But look, this is less than a volt. It's about 600 millivolts at the most. Right? That's all the controller needs to do to try and correct that. Here, where it starts going up and down, the controller starts to worry a bit more to get things on track. And here, there is a slight positive average voltage out of the controller, and again, only about 200 millivolts, because the green line, the feed forward alone, is braking too hard. Right? It's actually using the same constants as it does during acceleration, but braking is always easier than acceleration, right? Because it's friction and all sorts of stuff, and so it actually didn't have to work that hard. But not to worry, we have a controller just to make up that little gap. Okay. So how do we get these numbers? How do we end up in this being able to do these little bits of magic? What you need to do is to characterize your drive system. A DC motor is a simple beast, easily fed, easily abused. If you apply a voltage to it, it will run at a fixed speed. The speed that it runs at will vary depending on the load, but for any given load, the voltage determines the speed of the motor. That's the rules. If you want to change the speed and accelerate, you have to feed current into the motor. All right, and current generates torque. Now, we're not going to do the whole maths of motors, but this is the simple way to look at it. So consider, for example, that you have a motor running, or a robot running along on the flat. You fed it with 4 volts and it's doing 1 meter per second. But then it encounters a hill and has to go up the hill. What's going to happen? Well, it'll slow down, okay? Because the voltage is constant, but the load has increased, so the speed will decrease. If you want to get up that hill, in a car, you've got to apply more torque, and that would mean putting more current into the motor. So in order to go 1 meter per second up that hill, you'd still want 4 volts on the motor, but you want to be able to provide more current behind it. I don't know if that makes sense. If it doesn't, don't worry about it, because it's a distraction. But the rule, this is the rule, okay? Voltage determines speed, current determines torque. And the speed response is very simple, first order response. And this is the very same graph that we saw before, but I've added the equation this time. I mean, if you're not happy with the equation, don't worry, it's not critically important. If you do understand, that's fine too. So each of these is described by this equation that says the actual velocity as a function of time is the maximum velocity times 1 minus e to the power t over tau. And tau is the time constant. It's how long it takes for the voltage to go, let's say, from 0 to, 36%-ish? I can't remember now. 37% of the final value. So if the final speed is 1 meter per second, 30% of that is 300. And so on this chart here, we've done that. No, that's not right, is it? What's one time? Oh, well, one time constant is 63%. Yes, 63%. Buffoon. Right, so to get to 63%, which is about here, it's taken about 100 milliseconds. And this one up here, the same, right? So we got, 1,500-ish. 63% of that would be about 900. That's about there. Oh, look, that's 100 milliseconds. So these are all governed by the same numbers. The time constant is a feature of the system, and the maximum speed is a feature of the voltage. This tells you everything you need to know about your robot, and quite a lot more, actually. So if I take this speed and the voltage that generated that speed and plot them all on one chart, I get a plot that looks like that. So at 1 volt, I get about 200 millimeters per second. At 2 volts, 400 and something millimeters, nearly 500. At 3 volts, nearly 800, and so on. To go from 2 volts to 4 volts does not quite necessarily mean doubling the speed for peculiar reasons. But there are 2 things to note about this. One is the fitted straight line does not go through 0, right? So nothing at all will happen until the voltage gets to this value, because there's friction in the motor, stiction in the gears, and all sorts of stuff. You need a certain amount of volts just to make the things move. And if you're old enough, you may remember Billy Connolly talking about his big boots to take 2 steps or more before you even moved. Another thing to notice is this equation, right? This equation is the equation of this line, and it says that the speed will be 270 times the voltage minus 53, just to account for this here. And I draw your attention to this equation. I'll come back to it in a bit. Now, as it stands, it's not very useful because what I really want to do is to say, well, I want to go 1,000 millimeters per second. What voltage do I need? So it's more instructive to plot the graph the other way around. Right? You just collect these numbers from your record and plot them this way around. And so now I can say, well, look, if I want to go 1 meter per second, I have to apply a little shy of 4 volts. If I want to go 1,600 millimeters per second, then I'm going to have to go a little bit over 6 volts. So again, this is a surprisingly informative chart. One of the things it tells you is the top speed of your robot. Even if you haven't got to the top speed, this will tell you what the top speed is likely to be. If you've got 7 volts available on the battery, and if you can actually deliver all of that to the motor, which by the way you can't, but if you could, your top speed for this robot would be about 1,800 millimeters per second. And I would say that for a bog standard UKMARS bot with 20-to-1 motors, 1,600 millimeters per second is probably a likely top speed. So it tells you that. This intercept down here, right, this is saying that the speed will stay at nothing until I get to that voltage. And that voltage there, when you do the fit in your, you do a linear fit in your spreadsheet, is that. So it takes 0.195 volts before the robot will move. So this we call the static feed forward. And if you want the robot to move, add that voltage to everything, regardless, because otherwise nothing will happen at all. But for every millimeter per second that you want in speed, you multiply it by 0.00370 for this robot. And that will tell you what voltage. This is the equation that generated, I knew I shouldn't have done this, that green line, right? Except for the steps, I haven't forgotten. We'll come back to the steps. And if you remember the little bit of code that I showed you at the beginning, the code showed some fractions, 23 over 280 and 1 over 280. And that's because when I wrote it, I forgot to do the second step and put the numbers in. And actually, if I was to replace that code with the results from this robot, the numbers would be 1 over 270.4 and 52.3 over 270.4. Which if you was to sit down with a calculator, not now, because you should be paying attention, you'd find that 50 over 270.4 is that, and 1 over 270.4 is that. right? So they're the same numbers, just written in a different way. Right. So how do we actually get to use this? Well, we had a controller, and adding feed forward is just this one extra block. So I know what my set speed is, and I use that with the equations that we've just talked about to work out a voltage, a feed forward voltage, which will be the sum of some scaled constant and the offset voltage. I add that to the voltage from the controller, send it to the motor, and away we go. And it's that simple, right? And I know it's easy to just draw a diagram and say, hey, it's just a box on a control system diagram. But in fact, the code is also pretty simple. If we look at a part of the code that's in UKMARS bot, this shaded bit is that equation, right? So the output has been calculated already by the position controller. And then we get the speed that we want to be going. There's a little bit of shenanigans here about the fact that we've got a two-wheel drive motor, right? So we have to work out the speed for the left motor and the speed for the right motor. Just gloss over that. But we need to separate the outputs into left motor drive and right motor drive at some point, and this is where it gets done. And then I say, this is the same number. I could have equally applied it further up here. It doesn't really matter. It's my speed feed forward constant times the speed of the wheels plus the bias. And then I just send all of that off to the motors. So adding feed forward to your robot controller, once you have got everything else working, is really just these extra lines of code. That's it. That's all there is to it. In summary, if you want best control, I would suggest you should probably try to incorporate feedback control. You need feedback control for overall accuracy. They are, however, difficult to tune. Feed-forward controllers are really, really simple and do a surprisingly good job, but they can't cope with disturbances. So if your robot starts to run up a slope, the feed-forward controller, because it's just calculated a voltage, the robot will slow down. But if you've got feedback control in there as well, the feedback controller will compensate for that, and away you go. The combination of the two is remarkably effective, surprisingly effective, much more so than either on their own. Just as an aside, years ago when I was first doing all these things, I was trying to tune the feed forward and feedback control on one of my robots, and I couldn't get it right for the life of me. It didn't matter what I did, I couldn't quite get the response I was looking for, which, by the way, is this. Whoops, gone too far, as usual. The response I'm looking for, if you've got your feed forward and your feedback controller set up right, then for a simple run, if your controller output is close to zero all the way through, that's how you know that you've got it right. And I couldn't get it right. I couldn't for the life of me work it out. And the reason was because my test maze was sat on a bed in the spare room, and it was ever so slightly not level. Not by much. It was just a couple of inches too low on one side. And when it went one way, I got one set of results, and it went the other way, I got a different set of results. It took me ages to work that out, which was...
Yeah, so you got a variable load that you weren't compensating for.
Exactly, right? So the controller kept having to put inputs in, which I wasn't expecting, and so, I'd make a change to the feed forward, and then I'd get a different response because I was going uphill or downhill, depending. Anyway.
You could have compensated for that, but it probably just lose the spirit level.
Well, in the end, that's what I thought. It slowly dawned on me, and in the end, I did go and get a spirit level and went, oh, for goodness sake, But then I'm fussy, so.
this has happened at official competitions. I've had one of the IEE competitions in the mid-90s. My mouse was doing very odd things, and eventually we worked out that the maze on the floor just wasn't level. We went off and got a level, and it was a few degrees out, and it was making our mouse do all sorts of weird stuff.
Yeah,
well, now, of course, with the appropriate combination of feed forward and feedback control, these things will be a thing of the past.
Yeah, absolutely. I will also say that although this looks, it looks like you must tune this very, very finely. In the end, if you look at, say, how well HAL 900 ran at the main competition, that's running this software. It's doing this, but I did zero tuning to any of those things. So it's tuned up for Pete's mouse. HAL 900 uses different gearbox ratio. It's different weight. The wheels are different sizes. All those numbers should be different, but they're not.
Right. So
you make Peter cry.
No. What you've done is remind me. Unusually I wrote notes for all the slides, but more usually I didn't read them. One of the important points that I wanted to make, Derek has now made for me in a way, that one of the biggest advantages of this combination of feed forward and feedback is that it's much more robust, right? And that's why it works on a variety of platforms. I ran a mouse in Portugal, and it had 11-to-1 motors on it, right? Big difference. And I just swapped the gear ratio. In the config, I just changed the gear ratio. There's a setting for that, and ran it. And like Derek's mouse, I didn't retune anything. And the reason I didn't retune anything is because this combined control technique is very robust. So the constants will be wrong. Okay, but you have two things acting together to put it right. And so if you were able to look at the graph output for the robot with the wrong constants in, you'd find that the controller output is now much more busy. It's trying to do much more, something like the first example that I showed you, right? Because it's trying to compensate, and it actually may even be compensating the wrong way. So, for example, if your feed-forward control is set badly and is providing or is trying to provide twice the voltage that it needs to for that particular robot, then the feedback controller will go negative and subtract volts away from that to get it right. Okay, but the overall result is it'll still work, but it won't work as well as it could do. What I wanted to do tonight was to show a robot with 11-to-1 motors on, and I ordered some, but they only came today, and I didn't have time to set it up. But yes, Derek's observation is perfectly right, and one I meant to put in that there are two other big takeaways from the whole thing. One is the whole system is more robust, and so you don't have to get everything right. If you change something, you don't have to worry about it. And the other is, I made a lot of noise earlier about how hard PID controllers and PD controllers are to tune. And the great benefit of having feed-forward control in as well is it doesn't matter so much. If you get your PD controller wrong, it's not as important because everything will kind of sort itself out. So it's easy to do, and it provides you with a way of getting good performance with relatively poor configuration. Now, I will deal with that step, but are there any other questions or comments before I do?
Peter, first of all, thank you. Fascinating stuff. I had implemented by hand some PD controller. I had naively only put feed forward in as a static feed forward to basically get the thing moving in the first place. So I always had undershoot at the beginning of a demand move and overshoot as you reach the top speed, which I've seen coming out. I guess I've got quite a personal question to this, which is I'm just beginning to look at this half-size mouse, and I'm looking at worm drive motors, and I'm wondering how best to approach that. And I guess maybe I need to put them on and characterize them rather than assume they're going to work, because I have a feeling they're going to behave differently to a conventionally mounted motor. And I wonder if you've got any thoughts on that.
They'll behave just the same, but they will have a much higher gear ratio. Everything else will be very, very similar. If there is a difference, it will be the fact that they're much easier to break. That is B-R-A-K-E rather than B-R-E-A-K. Although, having said that, one of the reasons Tony always cites for not liking worm drive motors is that if anybody picks your mouse up and tries to twiddle the wheels, they're going to pull the gears right off it.
Yeah.
So no, it should behave essentially the same way. The current version of the UKMARS bot of the Maze Runner code has got a little instruction on how to get these numbers. There isn't. I don't think I left in the Maze Runner code something to directly do this. So, like, as I said right at the beginning, a lot of this is about providing people with a starting point. And so you need to write some code which puts a fixed voltage to the motors and blasts out speeds, measured speeds and set speeds as fast as you can. Don't put any timing loops in, just send them out as fast as you can. When you plot the chart, right, it's an XY chart, and so you don't need to have regular intervals, it'll sort itself out. And it's that, the characterization is that straightforward, really. It also raises the other point. I'm working on 2 new sets of code for MarsBot in a maze. One is just to run the maze with all of the frippery and faffing about taken out of it. And then another one will be, having put it that way, the frippery and faffing about and the maze stuff taken out of it. Right? So there will be a set of code for testing, setting up, and in this case, characterizing your robot, and then a separate set of code for running in the maze, having done all of the setup and configuration. And the reason for that is that the setup and configuration is also pretty valid for a line runner. And so that's, once you've got the physical characteristics of your robot, they are pretty much constant anyway.
The one I did have a question, sort of semi-related to the topic, which is to do with wheel slip, right? So you're measuring speed based on the encoders. Now, I know we've spoken about this before, but for a DC motor, I guess the maximum torque is at start, is it? So
Yes.
do you just control wheel slip by the acceleration profile, by limiting the acceleration? I mean, it's probably, I know Duncan's spoken about limiting the current into the motor to limit the torque, which is difficult to do without some piece of electronics to actually...
No, it's not really. A few things there. One is in general, if you accelerate and you get wheel slip, if you brake just as hard, you'll get wheel slip, but the other way, right? And up to a point, what you lose starting, you get back finishing, right? And in general, what I have discovered is that you never get back more than you lose, right? So if you say you tell it to move forward 3 meters, and you do that modestly with your granny shoes on, you'll get 3 meters. If you put the hammer down and tell it to just go for it, it will stop short. It never seems to overrun, right? So the one consequence of that is that within reason, within reason, you can always assume that you're going to be short of the finish point, not over it, and that allows you to do compensation. So, for example, if you've got a profile where I've left the slide on because I've got some more to do. If you run if you run up fast and hard towards a turn and then come down to turning speed, it's very unlikely you will have overshot the turning point. Right? So if you slow down to turning speed before the anticipated turning point, then you will only ever be even before that. And that's the importance of detecting the edges on the posts, because if you then wait until you see the edge of a post, you will almost certainly always be able to do that. Right? Now, you can clearly overcook this and end up in all kinds of trouble, but within reason. And the other thing is that with Decimus, I worked out, I do it mostly by limiting the acceleration. Through trials, you just work out that up to a certain acceleration, you get negligible wheel slip, and I just limit it to that because it's not really a big deal. Right? I know that Decimus can accelerate at, 2.5 Gs or something if I want it to, but I get slip, so I restrict it to, I forget what, but something under 2 Gs, because then I know that that's where the slip starts to become a problem. I could work out what it should be, I could compensate for it, but it works well enough without that, and there's on my list of small things to make a difference. I'm well into diminishing returns now for effort, and I haven't found the need to do it. So the other thing about current control is to do with Chris's question earlier about the step, right? So if everybody's agreeable, I will just have a quick look at why that step's there. So what am I on now? Slide 20. Let me just slip back and show you the step. So remember that voltage means speed, current means torque, and torque means acceleration. If I didn't need to put anything else into the motor, this green line here would end here and start here. Start here somewhere, actually. No, 0, that's 0. It would start here and go up there. And in fact, that would be parallel to that line there. Yeah? But it doesn't. There's a step. There's a small step just because of that bias. But remember, the bias was only 200 millivolts. But this step is the additional voltage needed to drive accelerating current into the motor. If I accelerated harder, this step would be higher. And if I accelerated more gently, this step would be lower. Does that make sense just as a statement before I go on? Nod or not? Yeah? Okay. And when it comes to brake, the same thing, right? You have to, it's a poor phraseology, but for lack of a better term, you have to suck current out of the motor, right? You have to have current going in the opposite direction to brake the motor, but nonetheless, it's current. It's accelerating current, decelerating current, so the step is negative and carries on down below 0. Because just before we come to a halt, we're actually trying to get torque in the opposite direction. So the size of this step is determining the amount of accelerating torque that goes in. And you might reasonably then ask, well, that's all very well, but how do you know how big that step should be? Well, it's actually easier than you might think. Look at this again, and consider what's going on at time 0. Down here, the motor's accelerating. And the faster we want it to go in the end, the harder it has to accelerate to get there. Yeah? So the slope of this curve at time 0 is the acceleration, right? Because acceleration is just the derivative of speed against time. Well, if we have a look at that equation here, that's the same equation that was on the graph. If we differentiate that, we get acceleration as a function of time is Vmax over tau, the time constant, times e to the minus t over tau. But at time 0, this is 1, and so the acceleration is just Vmax divided by tau. Right? And Vmax is the top speed and depends upon the voltage. And if you then plot, which I haven't, but because it didn't occur to me until around about 7 o'clock that somebody would ask this, so I'll just knock this out quickly. If you plot voltage against acceleration, you can calculate an acceleration feed-forward constant. And this is, so you know what your acceleration should be, and just like the previous stuff with the voltage feed forward, the speed feed forward, you just plug it into a simple equation, and this slope, by the way, of this is just the feed forward, the speed feed forward constant times tau, the time constant of the doodad.
Robot.
So lost all sense of speech then for a second. And the complete feed forward. So on my robots, I have a separate function for calculating the feed forward. And my acceleration, I don't know globally what the acceleration is. I calculate it from the change in speed, because when you're braking, you might change the acceleration. There are other ways to do it, better ways almost certainly. So I work out what the acceleration is, and then I apply my acceleration feed forward and the speed feed forward and the bias. So it's just one extra term on that equation to work out what the acceleration constant is. And that produces that step. So it's an extra voltage needed to drive current through the motor for acceleration and braking. So, Chris, that's the answer to your question from what feels like 3 weeks ago now, about why there is a step there. It's to drive that extra current in needed to do the acceleration. And this now is, that's just a PID controller in case anybody asked, but they didn't, so you can forget that. Right, now I'm done. Unless anybody has any other questions. Exhausted.
Quick question.
Yep.
Can you apply any of this to a schools line follower without encoders?
No. Yes. Well, I mean, if you've got a robot of a similar mass to a UKMARS bot, or if you can put motors with encoders on a test rig, okay, the constants are determined by the physical nature of the robot, its mass, the motor drive voltage, the gearbox ratio, and all that kind of thing, right? So if you can, all you need to do is to be able to measure the terminal velocity for a given applied voltage. And it doesn't matter how you do that, right? So you could, I mean, if you wanted to you could put it on a drag race track, put 2 volts into it, right? And set up 2 timing gates a couple of meters down the drag race track and measure the time between the gates if you wanted to. That would be perfectly reasonable. Remember, it only took 800 milliseconds, 500 milliseconds to get up to its terminal velocity. If it was a very heavy robot and had a very low gear ratio, it might take longer. But the point is, all you need to know is that terminal velocity against voltage, and it doesn't matter how you do it. And once you've got that, you can then, for that robot or any that are very, very similar, you can then get a decent estimate of the feed forward constant, and then you should be able to profile your speed more accurately than you might imagine. Certainly a hell of a lot better than just banging 5 volts out to the motors. The same thing applies to rotation. If you do it with rotation, it's a little bit more difficult, he said, struggling of a way to do it. But you could just set it to turn on the spot, right? Let it do 4 or 5 revolutions and just film it and work out how many degrees per second it goes for 2 volts difference between the motors or something like that. That should work.
Okay, thank you.
One more question, Peter.
Yeah.
Do you think feed forward would be a useful addition to the control loop for steering a line follower?
I've never tried it, but I don't see why not. I mean, it's the same kind of principle, but certainly one of the things that if you were on a line follower, if you were plotting the course and recording it as segments with different curvatures, then certainly a feed forward term based upon the anticipated rotational angular velocity during that term would be a good thing. It would have the same benefits as it would for forward motion. But in terms of the actual sensor value, I suspect not, because the error that you see is determined by how fast it goes and stuff. But on the other hand, do the experiment and let us know.
Yeah, I mean, I guess feed forward works because you can either anticipate the load or you've got a constant load. I mean, if you've got a load that you can't predict, then you've got to use feedback to control the system. But obviously, with most of these robots, the mass is fixed. We're running on a surface that's reasonably the same friction across it. It's got it's reasonably level. So it's mostly a predictable problem.
Mostly. But yes, really the application of feed forward in a line follower is twofold. One is the forward motion, because that's the same problem anyway. But if you course and you know that for this segment of the course you should be doing 50 degrees or 100 or 200 degrees per second, then you can calculate a value and give the controller a helping hand, because the controller output is a function of error, and so without an error there won't be an output. And if you imagine a line follower going around quite a tight curve, in order to get around that tight curve at speed, it needs a large error to generate enough turning voltage to do that, if that makes sense. But if you already know that you're going to need 2 volts difference between the motors to do that, and you apply it, then you're back to the same thing you were before. The controller now has a much smaller job to do because it's already going to be nearly there.
I'll come back to that one because a long time ago I tried to do that and it didn't end well. But I think I've been thinking about it more recently. Strangely, almost as reintroducing the integral term into the PID control, because you do know when you've mapped the course, you do actually know what you want to do, but actually a feed forward would be a better way to do it, and just let the controller detect it straying off the line.
I think so. The I term in PID controller is about long-term accuracy rather than prediction.
Yeah.
Yeah, the I term it's more suitable for the steering than for the actual control.
Yeah, but that's what you'd be doing on the line follower, right?
Exactly. Yeah, it's more relevant to that. The problem with the control is that you're changing it so much that it's always out, and the I term, because it ramps up, it then mucks things up because you've got this wrong value that suddenly needs clearing, and that causes steps. And
I would say that in general, unless you're doing speed control, right, which is because speed is a different problem, but for the kinds of things that we're talking about, a PD controller is what you want. The I term is a diversion. It's a third value which you have to get right, and your life's easier if you don't have to try and get that right. And as Derek said, there is no long-term. The point of the I term is to get a kind of long-term zero. It's there because if you've just got a PD controller, there is always an offset error, right? Otherwise, there's no output. The I term is there as a kind of fudge, if you wish. Controller experts can turn it in their graves now, but it's a kind of fudge to try and drive that error to zero over the long term. And if you're spending a long time without change in a line follower course, you're going very, very slowly. So I would say it's
okay. I will say, are we going to supply some way of actually calculating these values? Because from what I have experienced, it's quite easy to calculate the speed or the speed term and the static term, but the acceleration term is much more difficult to get right.
Well, I've got, funnily enough, I thought I had described this all before, and I went searching, and I haven't. But I did write it up, and I can't remember now why I wrote it up but never published it. I think maybe I sent it off to some people for discussion. I do have a PDF describing the whole process, which I can put up. And as I said earlier, once I'm reasonably happy with the what I'm choosing to call Maze Runner Core, right, which is just the maze part of the Maze Runner software, there will be, I don't know what I'll call it, UKMARS bot test or UKMARS bot config or something like that. There will be all of the test routines gathered together in one place, and I will make that test one of the things that's in there, and a description of how to use it. I also, if I didn't mention it at the beginning, I meant to say that there is kind of smoke and mirrors going on in the Maze Runner code. It's not complete. It's not complete for a variety of reasons, not the least being to generate this kind of discussion, right? So that people will find stuff and go, oh, that's interesting. The Maze Runner code does not have the acceleration feed-forward term in it. All of the graphs that I have shown you have come from my own code, which I use on my UKMARS bot. It's not in the Maze Runner code. The Maze Runner code only has the velocity feed-forward and the bias, and the acceleration feed-forward is left as an exercise to the reader to fill in the gaps, right? But I hope you've seen, with a bit of thought, it's not a difficult thing to do, and it's not a difficult thing to add. The whole point of the Maze Runner software was not to solve every problem, but to provide routes to the solution to most problems.
I think it also shows that for the feed-forward, they can all be treated separately. So if you put one of them in, you improve it a bit, but if you leave one out, the rest of the system compensates for it.
Absolutely. What I meant to do is the graph with the existing Maze Runner software, and I'm just going to sketch what I would expect to see. And so if that's the profile at the bottom, right, some strange angle, and remember with the feed forward, so that's 0, without acceleration, if the feed forward's the top one, right, has no steps to it, it just starts at 0 and goes up to whatever the voltage is, and the controller previously was just kind of wiggling along at 0. If you leave out the acceleration feed forward, the controller output will look like that. Okay, so at the start, I don't know, is that the start on your screen?
Yeah.
Yeah, right. So at the start, the controller will try to compensate for the lack of acceleration by providing a step. And then, going back to front here, and then once it doesn't have to accelerate, then that step will go away and you'll get 0 output because the feed forward sorting things out. And then when it tries to brake, the controller will provide that braking torque. So it'll all still work, right? But now the controller is filling in the acceleration portion.
Yeah. So presumably you could use that information to work out what the acceleration constant.
Absolutely. That's how I used to do it the first time before I had an epiphany about the equation and how to do it analytically. One approach is to simply do what I implied I had done at the beginning, which was to draw a straight line through the controller outputs, work out what the values are corresponding to those, and then just put them into the code, right? But that's actually harder than just doing a series of speedruns. But yes, it would give you the same result in the end.
Right.